I think there's already many people, so I suggest that we start. So
Great.
welcome everyone to this new QISS virtual seminar. Today we are very glad to welcome Stephen Wolfram, who is going to talk about his views about fundamental physics. So if you have short clarifying questions during the talk, please ask them. Otherwise, keep them for the end and we'll have plenty of time for discussion. So now, let's listen to Stephen Wolfram.
So I was told to summarize everything in 30 minutes, so I'll see what I can do. This is an increasingly large project which has spanned a long period of time, although only become intense in the last year or so. We also have Jonathan Gorad, I think, here, who is working on this and is the person to answer all kinds of technical questions in chat and so on as we go forward. All right, well, let's see. So I'll try and tell you a little bit about our big project and its current, as of this week, status. I think it's probably about the 1 hectophysicist level at this point in terms of activity being expended on it now. Let's see, so let me start off here. Well, let me give you a little bit of background, I suppose. Back a long time ago, when I knew some of you people in a different life, I used to be, back in the 1970s, I used to be a simple particle physicist and sometime cosmologist and so on. And so I kind of got to know all those methods at that time. And then in the early 80s, after I'd done a bunch of things, more practical kinds of things in computing, I got interested in sort of a big question about science, which is sort of how complicated things get produced in nature and elsewhere. And I kind of tried to use all those wonderful methods I'd learned in mathematical physics and kind of failed in doing that. So sort of got to the question of, okay, if I'm going to take the core ideas that we get from kind of mathematical physics, but generalize them, what do we end up with? And that got me started in the kind of idea of using programs instead of equations as sort of the raw material for making models of things. And that led, well, the most interesting thing probably was that I started kind of actually exploring the kind of computational universe of possible programs and just seeing experimentally what did they do. And so this is sort of a typical little experiment done on cellular automata. This is probably my all-time favorite science discovery. This is a cellular automaton called Rule 30. And the way it works is it's just a line of black and white cells and at each step, the color of each cell is updated according to that simple rule. So you keep running this for a while, and this is the picture you get. Now, at the time, and to my intuition, this was very surprising. It's like there's a very simple rule, and yet what you get is something very complicated. It's sort of not the way things are supposed to work. It's not the way our sort of experience in engineering tells us the way things work, and so on. But this got me started on a whole vast odyssey of trying to sort of build a new kind of science that was based on this idea of using programs as fundamental models for things, and then understanding the kind of general features of the computational universe of possible programs and what they do. And so that led to, well, a lot of investigation of this computational universe of possible programs and a lot of kind of efforts to find sort of general principles that govern the computational universe. And the most important one, which I'll probably mention a bit more later, is this thing called the principle of computational equivalence, which is sort of an overall characterization of what happens in the computational universe and has all kinds of fun consequences, like finally actually telling us how the second law of thermodynamics works and all sorts of other interesting things. And it's also a very important kind of foundation for what we'll talk about in physics. So I worked a lot on kind of what one could learn from simple programs and so on, and applied them in all kinds of different areas, and wrote this big book called New Kind of Science that came out in 2002. One section of that book was about physics, because once you've seen Rule 30, you can't avoid asking yourself the question, maybe the whole universe could work this way. Maybe there's some simple rule that is capable of sort of explaining everything we see in our universe. So the question is, how might that actually work? It's very clear that cellular automata in particular are not interesting or useful models for things like space and time and so on. It's also very clear that you had to kind of go below our current views in physics of space and time to sort of find something more fundamental that you could represent in some sort of computational machine code, so to speak. So I actually made quite a bit of progress on that in New Kind of Science, and I wrote this whole chapter 9 of New Kind of Science about physics and about ways to think about space and time and so on, and made all kinds of interesting discoveries there, including figuring out sort of how one can derive Einstein's equations from discrete underlying dynamics and things like this. So I published the book, and I would say that the response to the book in most areas was very positive, and in fact has led to a really quite wonderful transition from the sort of 300 years of work that's been done on the basis of equations, making models of things. Probably in the last 20 years or so, there's a pretty dramatic transition for new models of things that get made, and the things being things in, I don't know, biology, social science, whatever, tend to be based on programs, not based on equations. And that's sort of an interesting thing, and there's a lot one can learn about that, about how to think about those kinds of models from sort of the fundamental features of the computational universe. But the one area that people were profoundly uninterested in back when New Kind of Science came out was fundamental physics. It's like, we've got string theory, it's all good, we're going to figure out the fundamental theory of physics. We don't want any of this different paradigm stuff. So being a person who does practical projects, I was kind of like, the target market for working on physics doesn't want it, so I'm not going to do it. So I built Wolfram Alpha and Wolfram Language, and built a lot of things which I think are pretty important in the world, probably more important actually than the things I might have been doing in pursuing physics at the time. But anyway, I didn't pursue it. So years went by, and I kind of always had the intention of coming back and finding out, could these kind of underlying computational ideas actually have interesting and useful things to say about fundamental physics? Well, about a couple of years ago, I've been thinking about this some more and came up with a sort of a simplification which seemed important in the way that the sort of fundamental structure of these models worked. And then we have our annual summer school, which I recommend to people. And at that summer school, there are two young physicists, Max Piskanoff and Jonathan Gorard, and I'm talking to them about this stuff, and they're like, you have to work on this. This is too important to just set it aside for another few decades. So I said, okay, great. If you help me, I'll work on this. So we did. And to my great surprise, in kind of late 2019, we made an incredible amount of progress. And I think it's at this point pretty clear that we've got something which is a good machine code for understanding how physics works. And I think the thing which was a big surprise to me was I thought, okay, we've got this sort of new approach to doing things. It's going to be the new approach, and the old approaches are all going to be not interesting anymore. It's not the case. What instead seems to be happening is that what we are providing is kind of a low-level machine code, on top of which a huge number of the most popular kind of mathematical physics ideas that people have been pursuing for a long time fit. And they both inform what we're doing, and I think what we're doing perhaps clarifies and informs a bunch of the things that they have to provide. So it's really a quite wonderful thing. And I think there's a huge amount of fertile work to be done in kind of understanding the relationship between what we're doing and what's been done in existing mathematical physics. And people have started to do this, and can talk a little bit about some of the things that have been figured out there. So I think, so what is the basic idea? Now, I think we run these week-long study sessions which try to explain this. So I'm not completely confident how much I'm going to be able to get through here. But let me start off. Okay, so this is if you want to know more, there's this website, wolframphysics.org, which has thousands of pages of stuff, and there's a book that I even put together that is the various sort of at least my original papers about this stuff. But let me start off with giving kind of a approximate visual summary of what we're talking about. So sort of the foundational thing one starts with is, okay, what should the sort of data structure for the universe really be like? And I think that the thing one realizes, which I think you all know very well, is you kind of have to go below the usual notion of space in physics of just being this thing that exists, and it's this thing where you can pin real numbers anywhere you want and so on. You have to kind of go below that and expect that that will be something that emerges only in some kind of large scale limit. Well, so it's kind of and you also end up going sort of below our usual notions of time and so on. So what's the basic idea? This is kind of a rough summary, and then I'll try and go through more details. Kind of the notion is to imagine that the fundamental data structure is just a bunch of atoms of space, a bunch of points, you can call them. And the things I'm saying can be formulated in these kind of rather concrete terms of points and connections between them and so on. You can also use higher category theory if you want. It's equivalent to that. It's equivalent to various other kinds of formulations. It's a very kind of minimal model. It's actually a minimal model that is interesting as a model not only of physics, but of other things. Maybe I'll talk about that a little bit later. But kind of the idea is to start off just saying we have a bunch of these discrete elements. And the only thing we know about these discrete elements is how they're related to each other. So what we have is essentially a hypergraph that consists of a whole collection of relations between elements. So that's sort of the fundamental raw material that we're working from. So the idea is that everything in our universe should emerge as the large scale limit of this hypergraph. So so we can talk about how that works, and we can talk about how that hypergraph does things, how it evolves. So the idea is that there's just a rule that says that if you see a piece of hypergraph that looks like this, not this particular rule, but this is an example, if you see a piece of hypergraph that has some particular form, it should be transformed into a new piece of hypergraph. And by doing that, you end up building up this huge hypergraph. Maybe the one for our universe has maybe 10 to the 400 nodes in it. The large scale limit of this can behave like a manifold that is some, let's say, even integer dimensional space. Talk about that a little bit later. So kind of the notion is that the way that space emerges is from the limit of this hypergraph. The way that things like particles exist, they're essentially topological obstructions in the structure of this network. The way that things like curvature arise, we'll again talk about in more detail. It's kind of just a feature of the large scale characteristics of this hypergraph. And the thing I already knew back in the 1990s actually is that when you think about things this way, it's kind of a little bit like the derivation of fluid dynamics from discrete molecular dynamics. I happen to have worked on a very simple version of that with cellular automata back in the 1980s, where even just having a very simple cellular automaton rule, sort of thermodynamics is strong enough that that gives you sort of the same large scale limit as real molecules bouncing around. Well, so in this case, kind of the question is, when you have this discrete, there's all these atoms of space in this discrete hypergraph, what does the large scale limit of that end up being? Well, it turns out, and I already knew this in the 1990s, the large scale limit of that is Einstein's equations, which is really kind of cool. It's it's sort of the same kind of thing as happens in fluid dynamics, except that now we're sort of dealing with a discrete geometry rather than velocity field. Okay, so what I knew in the 90s was about vacuum Einstein's equations. I didn't really understand how to get energy momentum in this, and that was one of the things that we discovered in late 2019. But okay, so this is kind of a sketch of sort of how classical space might work. And one thing I should mention is, in this model, space and time are very different kinds of things. Space is defined by the sort of extent of the spatial hypergraph. Time is defined by this sort of inexorable computational process of rewriting pieces of this hypergraph. And so you might say, well, we know about relativistic invariance. How could it possibly be that a model where space and time start off being so different ends up having Lorentz invariance and so on? Well, turns out what you realize is, and again, I knew this back in the 1990s, that if you are an observer embedded within this universe, the only thing that you are going to end up being sensitive to is kind of the network of causal relationships between updating events. So every time one of these pieces of hypergraph gets rewritten, you can think about that as an updating event. and there's a causal relationship between one updating event and other updating events. It's as if each updating event is like a function, and the function takes certain inputs, and it can't run until it has outputs from another function that's going to be used as its input. And that network of causal relationships defines a causal graph for the system. And so an important fact is that with certain types of underlying rules, there is a property I call causal invariance, which is the property that it doesn't matter in what order these individual updates are done, the causal graph you get is always the same. And that causal graph is, and the fact that that causal graph is always the same is what leads to relativistic invariance. So even though the underlying system does not have it in terms of what you get by looking from the outside, if you're embedded within the system and you are only sensitive to this causal graph, when there is causal invariance in the underlying rules, the system will show Lorentz invariance. So that's the sort of first thing to realize. And over here, somewhere over here, one of these over here is a, oh, there we go. There's the space-time causal graph down there. Okay, so that's kind of the classical story. Now, the question then is, what about quantum mechanics? And is quantum mechanics sort of a glue-in add-on to the system, or is it something else? One of the things that I think is very wonderful is that quantum mechanics is not something you have to add in, it's something you can't avoid in the system. Because the point is that when you make these updates, there will be many possible ways in which these updates can be made. And so you can ask the question, well, which particular sequence of updates should we do? There might be causal invariance, which tells us we'll always get the same causal graph, but what particular sequence of updates should we do? Well, that's not defined by the model. And what we can think about is to make what we call a multi-way graph that shows the network of all possible updating events that can be done. So each node here, in this particular case, is kind of a global multi-way graph. Each particular node here represents the sort of full state of the universe. And this is a collection of different possible histories for the universe. What's notable is that you see branches and you see merges in this graph. And in the case of causal invariance, it is the case that with every branch, there is a subsequent merge, that the branches and merges are always eventually matched. But in any case, we can think about this big multi-way graph of all possible histories of the universe. And one of the things to start thinking about is sort of the obvious identification is these are all the sort of possible histories that correspond to the possible things that can happen, so to speak, in quantum mechanics. So one thing to notice is when we talked about causal graph for space-time, the question is, how do you reconstruct space from that causal graph? If you as an observer know only about the causal graph, how do you come to a conclusion about what space is like? Well, you have to do sort of a very Einstein-like construction of making the light cones and trying to make, you essentially have to foliate this space, this causal graph, and these individual slices of the foliation correspond to sort of instantaneous versions of what space might be like. And so that's kind of how you reproduce ordinary space from this causal graph. Well, you can ask the same kind of thing from the multi-way graph. What does it look like as you evolve in time in the multi-way graph? What do the sort of instantaneous moments look like? Instead of being space-like hypersurfaces, they're what we can call branch-like hypersurfaces. They're hypersurfaces that slice across the multi-way graph, representing possible views of what exists at a particular moment in time. And whereas one might use clocks to synchronize and light signals and things to synchronize things in space-time, here it's kind of using, well, actually I'm jumping ahead of myself here, using kind of interferometers to figure out what is a particular slice of a particular branch-like hypersurface. So the notion here is there's a way of slicing this multi-way graph to get these branch-like hypersurfaces. What is this thing that you get? What is the extent in the multi-way graph? It's what we call branchial space. And branchial space is effectively a map of quantum entanglements. So this branchial graph is two nodes in this particular case are joined if they have a common ancestor in the multi-way graph. So this is a map of kind of how things are entangled in the multi-way graph. And so what you find here is this branchial space is this kind of space of quantum states that is kind of complementary to ordinary space-time, but it exists when you slice the multi-way graph. Now, there's a sort of a combined thing that you get, which is you can get a multi-way causal graph which is kind of a combination space, time, and branch space kind of object, which becomes important when you start thinking about black holes and things like that. But for these purposes, we're just looking at there's this kind of notion of branchial space. There's this notion of foliating the multi-way graph to get your current view of branchial space. And that's related to kind of what observers of quantum systems perceive. And for example, you can think about quantum measurements as being associated with actually, I need to say a lot more to really get to that point, as being associated with these possible foliations of this multi-way graph. Well, so what kinds of things can we conclude? Let me just mention a few sort of bigger conclusions, and then we'll kind of zoom in a little bit more on more of the details of how this all works. So one thing I didn't mention is in space-time, there's a question of what is energy. And somewhat surprisingly, it turns out that there's sort of a bulk identification of energy that can be made independent of individual particles and so on. Energy is essentially a measure of activity in the network. And the way you measure activity in the network is a flux of causal edges. So every causal edge is representing kind of a causal relationship between two updating events. What you want to think about, and what turns out to be the identification of energy, is the flux of causal edges through space-like hypersurfaces. Momentum is a flux of causal edges through time-like hypersurfaces. So it kind of explains why energy momentum transforms the same way as space-time with that interpretation. So, okay, so energy is a flux of causal edges in this graph. When we think about GD6 in this graph, we'll realize that those GD6 are effectively deflected by the presence of those causal edges. Again, can go through many details of how this actually works, but the basic picture is a GD6 in this spatial hypergraph or a GD6 in the causal graph is deflected by the presence of these causal edges, this density of causal edges, which is what corresponds to energy. That's kind of nice because at least qualitatively, you start to see that's kind of like Einstein's equations. It's telling you that the deflection of GD6 is proportional to the presence of energy momentum. Okay, interesting in space-time. What about in multi-way graphs and in branchial space? Well, it turns out the exact same thing works. It turns out this multi-way causal graph that I mentioned, that there's an interpretation of quantum energy that is the flux of causal edges through now branch-like hypersurfaces. And so what ends up happening is that there's a deflection of GD6 in this multi-way graph that's caused by a flux of causal edges through these branch-like hypersurfaces. So in other words, what that's saying is, when you have a GD6 here, it is deflected by the presence of energy momentum. Okay, so what's the interpretation of the GD6 here? Well, the thing you realize is that when you think about quantum mechanics, you're used to saying there are quantum states. They essentially correspond to these nodes in the multi-way graph here. And these quantum states have a certain amplitude, which has a magnitude and has a phase. And just as I kind of think that the packaging of space and time as a single thing has sort of been a mistake in thinking about space-time, I think the packaging of amplitude, of magnitude and phase and thinking about quantum amplitudes is probably a mistake. Because in our models, the way that the magnitude arises for reaching a particular quantum state is essentially just a path counting in the multi-way graph. What's the interpretation of phase? The interpretation of phase ends up being position in branchial space. Now, one of the things that is a difficult piece of mathematics, still grappling with, although got a lot of interesting progress on it, is the coordinatization of branchial space. In other words, how do you actually assign phases to points in branchial space? So, when you do a double slit experiment, how do you actually figure out when the photon goes to one part of branchial space, so to speak, what is the corresponding phase? So there are a whole bunch of interesting mathematics associated with the coordinatization of branchial space. But the basic bottom line is that we think about position in branchial space as corresponding to phase. So what does this mean? This means what we're saying is that the presence of quantum energy, presence of causal edges in the multi-way graph, is causing a deflection of GD6 to be deflected in their position in branchial space, in other words, in their quantum phase. So rather nicely, that sort of reminds one of the path integral and reminds one of the fact that what it's telling one is that there is essentially a deflection of in phase of things. So the end result, which I think is really nice, is that in our models, basically, the Einstein equations in physical space are basically the same thing as the Feynman path integral in Branchial space. So in other words, this idea of deflection of JD6 by presence of energy and momentum, it works in both places. It's just operating in a different kind of space, in this case in Branchial space. All right, let me go in a little bit more detail and then try and get a little bit of a status report of where things are at. And then what I really want to do is have discussion, which I think will be more interesting than me kind of yakking about these things. All right, let me see if I can find some other. Okay, so this is sort of the story. Oops, is this going to work? That's not a good sign. Let's go to bring this up. Interesting. Okay. Well, if that doesn't work, there, something worked. Okay, good. Okay, so this is your typical hypergraph updating rule. Let's say you started off from a hypergraph that looks like this. You run it a few steps, you get something that looks like that. You ask yourself, what is the large scale limit of this thing? And you get all kinds of a whole zoo of different possibilities. But sometimes you'll get something you recognize. Like here's one that just kind of knits a very simple structure. It does it in a rather complicated way, but eventually it knits something that you might recognize as just a piece of sort of two-dimensional fabric, so to speak. So, and sometimes it knits things that correspond that you might think of as being, oh, that's like a curved space, sometimes a bit more exotic, and so on. So first question is, how do you measure things about these networks? So very simple way to measure dimension. You just say you start at a given point and you just ask, what is the size of the geodesic ball that you get by going, let's say, r steps away from that particular point? And so you can just measure that, and the growth rate of that geodesic ball, the exponent of that growth rate, it grows like r to the d, where d you can estimate as the dimension of the space. And I think Jonathan in particular has looked at much more elaborate estimators of dimension. I think this very simple-minded one seems to be a bit more robust than others, but you can kind of see how it works. That's for the particular system I was showing before. This is kind of how, this is as a function of the r distance. This is showing the sort of convergence of the effective dimension, in this case to about 2.6 of the limit of this hypergraph after it's evolved many steps. Okay, so when you do this kind of dimension estimation, there's a correction term that probably many of you know that is proportional to the Ricci scalar. And so in this particular case, you can determine, yes, this thing really is curved. It doesn't quite have dimension 2. It has a correction to that that's proportional to the Ricci scalar. So things get more elaborate when you're doing this for kind of light cones in the causal graph, but the same kind of thing works, and you can have the same kind of way of constructing essentially Ricci tensors, space-time Ricci tensors as this limit in these causal graphs. Okay, so that's a little bit on how that works. I mentioned kind of the updating of these graphs. This is a particular sequence of updatings, but as I say, there are many possible sequences of updatings that can happen, and that's what's represented by this multi-way graph. This notion of causal invariance, let me kind of illustrate that. Let's do it in the context of not a hypergraph rewriting, but just a string rewriting. And in a kind of puns become physics, I have a suspicion that the limit of these string rewriting systems is actually string field theory, but that is as yet unproved, and it will be a pun becomes physics kind of thing if that turns out to be true. But in any case, we can kind of use these string rewriting systems as kind of a simple proxy for what's going on. This is a typical example. We rewrite in all possible ways, and the thing that's notable about this picture is every time there's a branch, there will be a corresponding merge later on, and so we can start building up this causal graph. These are the events that correspond to those updatings. We can sort of join the related events. We can kind of go and actually construct the causal graph. In the case of let me show you how this works in the string rewriting system. So here's a possible way of applying the events in actually it's a slightly different string rewriting system, but it's a possible way of applying events. In this case, the string rewriting system is just reordering BA goes to AB and so on. And in the end, it will sort it but the order in which the sorting happens can be different. The thing that's important is that the causal graph, the graph of causal relationships between those updating events, is always the same, independent of what order you actually do the underlying updating events in. So those are three possible causal graphs. They're all isomorphic. Okay, what does the causal graph look like? In this case, the causal graph is ultimately just like this. We can ask the question, if we are trying to assign sort of what does space look like at instantaneous moments in time, we can kind of imagine foliating this causal graph, looking at those foliations. We can ask ourselves the question, what happens when we pick a different reference frame, when we pick a different foliation of this causal graph? Well, we could look at that. Let's see, where do I have a picture of this? Okay, so we can pick a different. Yeah, okay. So we can, if we say to ourselves, if we want our reference frame to just look like it's a sequence of time steps, space existing at each time, what will that make us conclude that how the causal graph is laid out? And it's just like this, and this is just like a standard Lorentz transformation. We can apply that back to the string rewriting system. And so this is essentially what the string rewriting system looks like in a boosted frame. And what's kind of interesting is that you immediately see time dilation even happening in the string rewriting system. You're kind of trading off visiting more places in space for progressing in the evolution of the thing in time. So in a slightly more realistic case, this is even still a very junior version of what the actual causal graph looks like for one of our systems. They end up looking considerably more complicated than this. But this is kind of how you start to think about foliating this causal graph and making these things that correspond to sort of instantaneous versions of space. Well, let's see. We can talk about the corresponding foliation for the multi-way graph. That's a foliation of the multi-way graph. That's kind of what a quantum measurement looks like, what some version of a quantum measurement looks like in this situation. And this is a version of kind of what it kind of looks like to, oh, actually, this is a better version. This is kind of a black hole in Branchial space corresponding to, let's preserve that qubit without evolution of a choice of reference frame and so on. Okay, well, so let me give you a little bit of sort of an update of things that have been figured out. So we've been interested in working out sort of how does all of this connect to existing things we know. We understand. Let's talk about two sides. We'll talk about the general relativity side. We'll talk about the quantum mechanics side. On the general relativity side, there's a question of kind of looking at. Well, I think the best way to kind of see what's going on there is probably a paper that Jonathan just wrote that, let's see if I can pull this up, that just got uploaded. So let me see. I wonder whether it's here. Look at that. That's good. Okay, there's my most recent thing from a week or two ago is about multi-way Turing machines, and that has to do with understanding quantum measurement, but we'll not talk about that. We'll talk about Jonathan's thing here, which is an attempt to use our models as a practical discretization for general relativity. So kind of what I did back a long time ago with fluid dynamics was I made this cellular automaton, which was not intended to be a realistic model of molecules, but from which in the large scale limit, you can get fluid behavior, and people use it these days as a practical method for doing fluid dynamics computations. So the idea here is, what if we take our models and we just say, let's use them as a sort of practical system for doing computations in general relativity. And so what Jonathan did was first sort of scaffold it using causal set theory, and we kind of have an algorithmic way of sprinkling elements in causal sets coming from our models that kind of, but then to remove the scaffolding and say, let's go straight from the underlying dynamics. And effectively what we're doing is, this is now sort of a proof by compilation. It's showing, yes, you can actually get the things that you expect in the actual Einstein equations. And what is this? This is, okay, this is, oh yeah, this is, and what happens, by the way, an important feature of our models is that space does not have to be fixed dimensional. The dimension of space is a dynamical variable. And so, for example, we suspect that in the very early universe, space was effectively infinite dimensional and only gradually sort of cooled down to be roughly three-dimensional. And that means that, for example, we can perhaps expect to see dimension fluctuations, and we're trying to figure out what the consequences of dimension fluctuations will be for the cosmic microwave background and so on. But one of the things for general relativity is that you can actually see topology change dynamically happening in the actual evolution of these models. So this, I think, is the pieces of the Schwarzschild solution, but I think there might be a better picture here oh, look at that. Is that directly from our models? I think so. That may be still scaffolded by from causal set theory, or it might be, I'm not sure if this is, I don't know Jonathan's paper, so probably it's still scaffolded there. It probably have to go further down here to see the results of just going directly from our models and looking at the comparatively large scale limit. I mean, what we can compute on an actual practical computer is much less impressive than what the universe can compute. But we can still do things like we can find the causal graph associated with two merging black holes, and we can see them actually doing their merging, and we can compute the ring down of the black holes and so on. We can also start seeing fun things like when a black hole becomes supercritical, what happens, how actual pieces of space-time start breaking off and so on. And that's something we can see in our models because we have the ability to have topology change. So that's something on that sort of a latest thing on the general relativity side. On the quantum mechanics side, I can also quote things that Jonathan has been up to. Well, let's see, there's a whole lot of stuff to do with the kind of understanding branchial space and understanding how things work there. And this is a more sort of idealized model, multi-way Turing machines. I'm sorry? Sorry, somebody was saying something. Somebody want to say something? No? Okay. All right. So anyway, this was last week's effort from me about understanding essentially the structure of branchial space in the context of the very simple case of a multi-way Turing machine. Another, let's see, all kinds of things here. Okay, this is another direction. This is on the quantum mechanics side. Jonathan, Mano, Xerxes, working on connecting our work to categorical quantum mechanics and showing, and I think now we have a nice automated proof that yes, our model is equivalent to ZX calculus, to categorical quantum mechanics, which is also equivalent to standard, von Neumann style quantum mechanics. So I think from that, we can kind of know that, yes, it really is the case that our model reproduces ordinary quantum mechanics. And there are many sort of pieces to that, and there are many questions about, for example, in our models, we don't just say, oh, and then a measurement happens. We actually model the dynamics of the measurement. And so the various different interpretations you can give about how measurement works and how you're picking these kind of reference frames, these quantum observation frames. There's sort of a question of how you conclude that definite things have happened in the universe. How do you get objective reality in quantum mechanics? And this causal invariance idea is a key part of that. But something that we think is the case, Jonathan has been very much a proponent of this idea of kind of the completion interpretation of quantum mechanics, that essentially observers are effectively making identifications between branches in the multi-way graph. And they're doing that in sort of an observer brain is kind of spread across pieces. Okay, so the thing to understand is just as the understanding of space-time comes about from thinking about the observer embedded within the system, which is evolving, you have to think about that in terms of quantum mechanics. So what you end up having to think about is how does a branching brain perceive a branching universe? And in order for a branching brain to have sort of a consistent view of what's happening in a branching universe, it effectively has to do these completions that effectively say these two branches I will consider to be equivalent. Now, if there's causal invariance, eventually those branches will turn out to be equivalent, but the brain can kind of assume they're equivalent more quickly. Now, that idea So once you think about that, you kind of start realizing you can actually make explicit models of quantum measurement and so on. And we haven't brought this to a full conclusion, but it's looking like we can actually understand in the case of quantum computing, you know, you're kind of branching out in this multi-way graph, and then to know what actual result you got, you have to kind of complete things back to be able to see what the definite kind of classical result was. And so you can kind of see what the trade-off is between sort of the advantages from branching and the cost of doing that remerging. So that so one of the things happening there is using our formalism to basically make a better way to do actual things like theorem proving in quantum circuits by translating the quantum circuits into multi-way graphs. And we actually have an explicit translator, you can find it in our function repository, an explicit translator from standard quantum circuits into multi-way graphs. And you can then do the computations in multi-way graphs and then go back to get the standard results from quantum information theory. We don't yet know about quantum field theory. The thing that is the next big hope is to be able to take what we're doing for general relativity and be able to do that as a practical way to essentially discretize quantum field theory and make a proper kind of Minkowski space version of something a bit like lattice gauge theory, but not really like lattice gauge theory. So then, and I should say, by the way, on the story of you know, finding particles and so on. So we're sort of slowly, we've understood energy, we've understood momentum, we've sort of partially understood angular momentum. We kind of know how that roughly is set up. We don't yet understand the quantization of angular momentum. We're trying to figure out, we suspect that it has to do with a whole story of holonomy and homotopy in these multi-way causal graphs, and it might have some connection to twistor theory and things, but we don't yet know quite how that works. We have some sort of toy models of that. When it comes to local gauge groups, it's actually very much the same story. We can start, okay, so one of the things we have to do is essentially build differential geometry on top of our hypergraphs. And ordinary differential geometry is built in integer dimensional space. And so the question is, what does things like Riemann tensors look like in fractional dimensional space? Well, we finally actually have a way to answer that by looking at them as limits from these hypergraphs. And we're starting to understand sort of what's underneath tensor indices. How do tensor indices get built up from many sort of equivalence classes of paths in these hypergraphs? And so as part of that sort of program of sort of building up differential geometry and so on, we think about building up fiber bundles, and we can see how we can get local gauge groups. And we have at least toy versions of this where you can see sort of the emergence of local gauge invariants, just as you can see the emergence of kind of continuum properties of the underlying space. So this is, but we don't yet know how, we don't understand yet things about, you know, we have suspicions about how quantization of angular momentum works and so on. We don't yet know that. A thing that I should say in general is there's sort of a question of how generic and how specific are the various things that we're seeing here. So one of the things is,
Wolfram,
yes,
that you can wrap up in the next 5 minutes so that we have plenty of time for discussion.
Okay, I could stop actually, and we can. I was going to say, I'll say only one thing, which is kind of the question of sort of how generic and how specific is what we're seeing. So this phenomenon of computational irreducibility, which sort of afflicts many systems in the computational universe, most systems in the computational universe, that even if you know the underlying rules, to figure out how the system will behave involves an irreducible amount of computation. So for our universe, that's sort of an unrealistic amount of computation. And I have to say, when we started this project, I thought we'd be very lucky if we could reproduce the first, 10 to the minus 100 seconds in the evolution of the universe and forget about getting things which were actually readily connectable to existing physics. But I didn't count on sort of the strength of what amounts to the second law of thermodynamics, the strength of the fact that even when there's computational irreducibility, it actually implies a certain sort of regularity to systems. And the thing we realized is that there's underlying computational irreducibility about the specific updates that are happening. But there's always, when there's computational irreducibility, there are kind of slices of reducibility. And there are two big slices of reducibility that we can identify in the case of our models. Those two big slices happen to correspond precisely to general relativity and quantum mechanics. So effectively, general relativity and quantum mechanics are the generic things, just like one gets generic fluid equations independent of shapes of molecules and things. They are the generic features of models of this type. And so there's a question of sort of how far can one go generically? Can one get to specific gauge groups generically? What can one get generically? And for what do you have to know the underlying rule? I should say another thing about that is a thing I'm not going to talk about. I'll talk about if people are interested. There's a question of why one rule and not another. It turns out that there's a generalization of the multi-way graph we call the rule multi-way graph, in which you're thinking about all possible rules operating. And what you then realize is that, in fact, the universe can be thought of as something which is operating all possible rules. And we are essentially a particular reference frame that corresponds to the way that we describe the universe and we do physics, is the one that makes us assign a particular rule to what we observe. I might also mention that the whole formalism that we're dealing with is rather nicely applicable not only to physics, but also to distributed computing. And you can make very nice correspondence between a lot of ideas in distributed computing and ideas in physics, including importing a lot of powerful ideas from physics to distributed computing. It's also relevant to mathematics, because we can think about this network, this multi-way graph, as like the graph of creating all possible theorems in mathematics. And so one of the things that I've been particularly interested in recently is what is bulk metamathematics? What does the physicalization of metamathematics look like? What can we understand from the correspondence between things we understand in metamathematics and things we understand in physics? How do those kinds of things correspond? And I'll stop there. And that was a rather overly quick summary, but hopefully I didn't forget too many major points. And please ask questions.
Thank you very much, sir, for your nice talk. So I'm sure there are plenty of questions. So to all of you who want to ask questions, please raise your hand in the chat, and I will take your name and then tell your name when you can ask the question. So I see already 3 questions. So first, maybe Carlos, then Lee, and then Alex Kissinger. So please, Carlos, ask your question.
Right. Hello, Stephen. Thanks very much for the talk. That was amazing. Can you hear me now?
Yeah, we can hear you. Yeah,
sorry.
Good.
Yes. Hi, Stephen. Thanks for the talk. That was very, very interesting. So most of the pictures and illustrations of the networks use this pairwise edges, but obviously you mentioned it's a hypergraph. So could you mention a little bit the intuition or say a few words about what's going on with higher order edges and in general, sure. I mean, what it's, anything.
The reason that hypergraph, that it's important for it to, well, let me show you. I'm sure I've got pictures, plenty of pictures. Let me just pull up some pictures of, let's see. They're just a little bit more, okay. There's your average hypergraph. Those are ternary hyperedges. And you can, it's just a little bit more difficult to draw. The reason, when I was working on this in the 1990s, I worked on pure graphs, and I wanted to have the simplest graphs, and so I had trivalent graphs. And the problem was that when you have pure trivalent graphs, it seemed very awkward to me that not all possible rules that you might write down were plausible rules. Because, for example, you can end up with a rule where you have a lower symmetry graph going to a higher symmetry graph. Truth is, now I understand that even if you had that, you could just think of that with different edges in the multi-way graph. But back in those days, I didn't really understand that. And so I thought that having this idea of just having trivalent graphs had this problem that sort of any old model you wrote down couldn't be a plausible model. You have to pick models specially, like picking only prime numbers or something. With hypergraphs, the way this works is any possible, so a typical rule has the form, I don't know, you can represent it as a hypergraph, but this is just a rule that says anytime you get XY, you replace it by XYZ, or let's find a more non-trivial rule. Let's see. Let's see. Well, yeah, here's one. I mean, so this is just saying, again, this is an ordinary rule. I can show you. Well, what are these? These are the numbers of rules with different kinds of, so the ones with a little 2 subscript, those are binary edges. These are ternary edges. it's the main thing is sort of the robustness of the model is greater when you think about things in terms of hypergraphs. It's the natural extension of it's sort of the naturally occurring version of this model. If you force it into ordinary graphs, you kind of don't get the sort of the natural version of how to set up a model like this. But I don't think there's anything much more in terms of the large scale limit of the system. It doesn't make any difference. And the truth is, I could have figured out everything we figured out just in terms of trivalent graphs back in the 1990s, except that I didn't have certain other ideas that have been important in figuring all this stuff out.
Yeah, I mean, it makes a lot of sense to things in higher order, in my opinion, as well. So is there any structure at all on the graph other than the connection of and the edges? Are you assuming any other structure? Okay.
No, absolutely not. I mean, everything emerges. So the whole point is, the fact is dimension is just a consequence of the large scale structure of the connections and everything. And when you have a particle, for example, it's sort of a toy version of that is, imagine you're dealing with planar graphs and imagine that you're doing updates which preserve planarity. In the case of planar graphs, we know what the sort of lump of non-planarity looks like. It looks like a particular, the K33 subgraph. And so that is our topological obstruction that corresponds to our sort of preserved particle-like structure in that very toy version of a planar graph being rewritten. We don't know, we'd love to know how topological obstructions work in fancier graphs. I've asked this to graph theorists for many years. My favorite answer from a well-known graph theorist was, come back in a century and we might have more to say. But unfortunately, in doing physics, one has to barrel forward and try and figure things out independent of those kinds of obstructions to obstructions, so to speak.
Thanks very much.
Lee Smolin, would you like to ask your question?
Hi, Stephen. It's beautiful. It's wonderful talk and wonderful stuff, and I look forward to understanding more about it. So this is a question which I'm intrigued by because of the analogy between the space-time and the computation. And I want to know how deep that goes. So I want to know, do you have universality of computation, so that just like in the game of life, you can embed universal computation? Can you embed universal computation in a space-time? And if you can, is there an analog of the Gödel theorem? Maybe that not every state has an evolution.
Yeah. This is what you're talking about is kind of a foundational brick in this tower that I've been trying to build for a long time. Okay, so the thing about this principle of computational equivalence that I mentioned is this observation that came out of studying the computational universe, that if you look at different computational systems, basically as soon as those systems behave in ways that aren't obviously trivial, they end up being capable of computations as sophisticated as anything, in particular for universal computation. So we know a bunch of examples. So I'll give you, I'll pull up one, for instance. Let's see if I can get that. Let's see. I mean, we have many examples of this now, but one that was kind of fun from a little while ago was this is the very simplest universal Turing machine that I had kind of guessed had to be that way, and somebody proved it back in 2007. This is sort of a typical example of the operation of the principle of computational equivalence. As soon as the system behaves in a non-trivial, in an apparently non-trivial way, it will turn out to be as computationally sophisticated as anything. So one feature of being computationally sophisticated is that when you imagine, if you imagine kind of you are you're an observer and you are trying to let's see, why is this not doing this? Sorry, I'm just yeah. So you are trying to compute what's going to happen in a system like this. So you might say, I'm very clever. I've got a brain. I've got I can do more sophisticated computations than a system like this. Surely I can jump ahead and figure out what the system is going to do.
Right.
But the principle of computational equivalence says you can't do that, because your brain is ultimately computationally equivalent to a system whose rules are as simple as this. So the most significant thing here is this idea of computational irreducibility, this idea that you kind of can't expect to jump ahead. Computational irreducibility, that's sort of the bad news about computational irreducibility. The good news is it leads to a kind of a form of ergodicity that allows one to make continuum limits and allows one to conclude things like, that's why there is a notion of continuous space. Because the reason there's continuous space is the same kind of reason as we think fluids are continuous. It's because those molecules are bouncing around in very random ways. And we can kind of understand the second law of thermodynamics, for example. The second law has been kind of confusing. What is a valid coarse graining procedure, for example? Well, the answer is you should think about it as you've got that initial condition for the gas, the thing bounces around, does what it does, and then when you are looking at it, you as an observer, you as a computationally bounded observer, you can't go back and sort of cryptanalyze what the gas did. It has basically done enough computation that as far as you're concerned, what it has done will seem completely random. And it's the same exact thing that's happening in these systems too. And so in our model, the fact that the passage of time is the inexorable, computationally irreducible process of computing one state of the universe from the previous one. Now, there are lots of consequences. I mean, when you start asking about general relativity and you start asking about the construction of reference frames and questions about, the cosmic censorship hypothesis and so on, those things end up being closely related to all these questions that are kind of like, well, the computational irreducibility is a much more fine-grained version of the same ideas that go into Gödel's theorem. I mean, and so for example, when it comes to asking, can you create a reference frame that has all the right features to let you conclude something about space-time? If you are a computationally bounded observer of space-time, that puts certain limitations on what you can construct, and that's what leads you to conclusions about how things work in general relativity. So yeah, there's a wonderful collection of connections here between sort of these foundational ideas about computation and things you can conclude in physics. You can start asking the other way around. You can ask about, when you do distributed computing, you can ask about essentially programming in different reference frames. You can ask about event horizons in distributed computing. You can ask about event horizons in metamathematics, which is also quite interesting, and the role of the role of kind of singularities in metamathematical space and so on. It's really once you have this kind of underlying machine code, you realize that it's quite it's something where you can, it's sort of a model onto which you can attach lots of different kinds of things. And I think that the way I kind of view what we've done is if you know the early history of computation, back in the 1920s, people were starting to invent things that actually do correspond to universal computation, but nobody understood that at the time. Then Turing machines came along, and that was a sort of fairly concrete, explicit, understandable version of how you think about computation. And then all these other ways of thinking about things that turn out to be computation turned out to be equivalent. And I think what we have here is sort of the simple-minded kind of concrete version of how you think about constructing things like space-time, and on top of which you can kind of connect lots of kinds of things that people have thought about. So that's a rough summary. I mean, this is the kind of the figuring out of the consequences of the computational paradigm is kind of my life's work. So there's much to say about that topic, but that's a very quick summary. So.
Great, thank you. I look forward.
Alex Kissinger, would you like to ask your question?
Yeah. Hi, Stephen. So it looked like this this notion of causality that you introduced between rule firings. If I understand it right, it's that a causal link between rules is that a certain rule creates a node in the past or an edge in the past that a future rule needs in order to fire. Is that
Yep,
right?
Exactly. That is correct. Yes.
So this looks a lot like notions of causality coming from models of concurrency, like Petri nets.
Yes, it does.
Is that something that you and Jonathan have looked at?
Yes, we have. I mean, Petri nets have always struck me as a bit overcomplicated, but and I think that but yes, there there are certainly relations. I mean, I think that so our multi-way graphs can be thought of, so Petri nets are like resource-bounded multi-way graphs. So a multi-way graph, you just look at all these possible cases. In a Petri net, you're saying, let's only have a certain number of tokens that can get used up on this path in the multi-way graph. So actually, you can think about, for example, think about chemical reactions. You can think about chemical reactions, which were the original motivation for Petri nets. Multi-way graphs can also be thought of as a model for networks of chemical reactions. So you can kind of start seeing how things work there. Now, the question that we'd really like to know more about is the branchial space of Petri nets. And I think there's recent work, and I recognize your name, and I think maybe you've been involved in this, because I mean, there's some recent work that seems like it's heading in the direction of being able to say things about what for us is the coordinatization of this branchial space that's kind of the slice through the multi-way graph of all possible evolutions. Maybe Jonathan, do you have a crisper thing to say about this?
Well, I was just going to mention that you could show up some multi-way Petri nets if you wanted to.
Okay. If you send me a multi-way Petri net, where are they?
Oh, sure. I think I emailed them to you a while ago, but I can re-email them to you.
That's, yeah. Well, okay. Yes, there is a close relationship, and we'd like to understand it better. And I think it's really interesting. And I think that there's a sort of a whole class of things. So we can also mention something about the relationship between multi-way graphs and category theory. So you can think about kind of when we're dealing with the individual edges, we can think about that as sort of being a one category. When we think about these causal graphs, it's kind of like a two category. When we think about the different possible foliations, it's kind of like a three category. We can think about a thing when we talked about this rulal multi-way graph, that's actually an infinity category. And one of the things I thought I would never have a reason to understand the whole Grothendieck infinity groupoid business, but I realized that that's actually our rulal multi-way graph is a concrete version of this Grothendieck infinity groupoid. And there's sort of questions about what can we learn sort of coming down from this rulal multi-way graph and looking at these foliations of the rulal multi-way graph, and how can we use the ideas of Grothendieck's hypothesis, for example, to deduce things about what we see in kind of slices from what we know about the infinity groupoid. But yeah, a lot of really interesting things there, and we'd be interested to talk more about this stuff.
Okay, Lachlan Gray, would you like to ask your question? And then there will be Bob Corker.
Hi, thanks. I'm a really big fan. And so I was wondering if it's possible to, or if it would make any sense to use these rules to model things other than fundamental physics. I was thinking like maybe using it to mine intelligent programs or something like that, if anyone's tried that. Or,
so the answer is absolutely yes. I didn't see this coming, but it's absolutely the case. It's a little bit analogous to cellular automata. So cellular automata are essentially minimal models of parallel computation when you've already burnt in your notions of space and time. And it turns out cellular automata get applied to modeling all kinds of things. I mean, road traffic flow, chemical catalysis, things in all kinds of different things, because they are essentially minimal models of a particular class of structure. These models also turn out to be minimal models, but now they don't have a built-in notion of time. They don't have a built-in notion of space. That all has to emerge. So the things which we've looked at so far, distributed computing is a great case. And all of these things about, for example, race conditions in distributed computing are the same story as the uncertainty principle in quantum mechanics, and the same story as the sort of failure of what's it called? The fact that there are Riemann tensors, that are non-zero Riemann tensors from making little rectangles, in the failure of commuting in space-time, failure of commuting in quantum mechanics, failure of commuting in distributed computing in race conditions, those are all the same thing. And you can see that in these models. I mean, I think that so yes, it's interesting to look at this in terms of distributed computing. One of the challenges there, since I spent my life as a language designer, it's one of the challenges is, can we use these ideas to have a human understandable way to think about distributed computing, which we previously had a very hard time with. And I think that importing ideas from physics, particularly ideas from general relativity, maybe some from quantum mechanics as well, it's going to be, there's at least a fighting chance that we can have a sort of a human understandable way to think about asynchronous distributed computing. Now, there are other places this can be applied. Another one I've been interested in recently is molecular scale computing, because one can think about these graphs, as I mentioned, as being graphs for chemical reaction networks. And there are questions about how to use that as a sort of practical way to do computing. That thing I just wrote about multi-way Turing machines is a story of, usually when we think about computing, we think about one input, one output. You type an input line in some Wolfram language notebook or something, and you get an output line. But in these multi-way graphs, computing has a different character. You have a cluster of things in branchial space leading to a cluster of things in branchial space in the output, and how to think about the sort of the structure of programs of computation that way. There are other applications as well. There's some people who've been trying to apply these models as models of biological evolution, and that has some rather interesting features as well. There is also some, what am I forgetting? Well, metamathematics is another big area where the kind of this multi-way graph represents the graph of possible theorem provings that can be done. But yes, I think it's a really, there's lots of interesting things there, and the actual structure of these models is very interesting, and as is often the case, in the end, these models look like a zillion other kinds of models. There are formulations of them in category theory. There are probably algebraic formulations of them. There are a whole variety of different formulations because they're very minimal models. And so it's sort of not surprising that there are different ways to formulate them. But in terms of doing searches in the computational universe for programs that do interesting things, actually, nobody has done that yet, to my knowledge, for this class of programs. People have done that lots for things like cellular automata and so on. But for this class of programs, that hasn't actually been done. And it's a good idea, and somebody should do it. So yes, actually, I suppose to some extent what Jonathan was doing recently in searching for rules that do a good job of reproducing general relativity, do an efficient numerical analysis job of reproducing general relativity. That's an example of sort of searching in the space of these models for ones that, in a sense, have good convergence properties for purposes of doing numerical relativity. Another.
Bob Coker, would you
yes,
like to ask?
I kind of had exactly the same question, but I had a different example in mind, which I was thinking about, like things like concept formation cognitively and things like that. To which extent this can be applied to something like that?
Well, let's see. I've thought about those kinds of things a lot. I think that when it comes to things like understanding meaning space, understanding the space of possible meanings of things, there are certainly, the answer is I don't yet know. I think, I don't know yet. I think there are interesting things to think about there. There are interesting general ways to think about kind of, this as models for data. I mean, just like, neural nets are today's most popular kind of model for data, there are other kinds of models for data that are more related to multi-way graphs than related to the, so you can also think about multi-way graphs as if you imagine a neural net and you imagine sort of all possible paths for the choice of weights, you can think about that as corresponding to a multi-way graph. And maybe you can think about some things in terms of understanding the performance of neural nets in terms of multi-way graphs, but this is not yet worked out. And so possibly yes, but I don't know yet. I would say that my own, the way I view, so just to say sort of big picture point of view about meaning and things like this, the thing that's amazing about the computational universe is how rich it is and how many different kinds of things can happen in it. Many of the things that can happen are things that we humans absolutely don't care about at this point in history. We look at some cellular automaton, it's doing amazing things. We say that's a cool picture and we don't care. So we have a certain set of things that we, through our sort of culture and development and so on, actually care about. Those are the things that we might have words for in our languages and things like this. the role of a computational language designer, which is what I spend most of my time doing, is to make this bridge between what we humans care about and think about and what's possible to do in the computational universe. And I kind of view this project as well. So that process is, there's all these things, this sort of ocean of computational possibilities, and then there's the kind of the things we care about, and that's and you know, in making a computational language, you're making a way of describing the things we care about in a way that can be operated in the computational universe. Now, so in a sense, you're taking this vast ocean of possibilities, and you're saying these are the things humans care about, and this is how we can characterize them. This is how we can set up a structure, a notation. I mean, I kind of view the sort of effort of making a computational language as kind of the analog of what people did about 400 years ago in making mathematical notation, which is what kind of got mathematical sciences launched. It's kind of, we're trying to make the sort of the computational analog of that, notation for computation that humans can understand. Not all possible computation, because there's a lot that we humans don't care about, but computation that we humans care about. So for this project, a sort of philosophical view of this project is there are actually now three entities that we're thinking about. There's the computational universe of all possibilities, all possible computations. There's us humans with what we can think about, and there's the physical universe doing whatever it does. And so in a sense, the role of this project is to find essentially a language which allows us to connect those three things, that allows us to have a description of the physical universe in a form that we humans can understand through computation. And so it's kind of a, you know, it reduces the problem of finding a model for physics to a problem of language design, effectively. You're trying to find, and by the way, this whole idea about rule multi-way space and so on, and the space of all possible rules and such like, kind of gives us the indication that, you know, the physics we have is not the only physics one could have. The physics we have thinking about space and time the way we do is not the only conceivable way to describe the universe. It is merely one language for describing the universe, and one that fits in with us based on the history of our development of our thinking. So that's kind of maybe a big philosophical view of what we're trying to do.
Hilaire, would you like to ask your question?
Hi, and thank you very much for the very interesting talk and very elaborate theory, which is nice to hear about. So I've got a question about superpositions. So the first part I'm interested in is to understand how superpositions in general of quantum states arise in this theory. But secondly, I'm also wondering if in your theory it is possible to construct superpositions not only of quantum states but also of for other like higher order phenomena, for example, quantum causal order. So maybe I don't know if you've seen the recent works in quantum information and foundations on indefinite causal order and superpositions of causal orders. And if so,
I haven't, but maybe Jonathan has. But I mean, to answer about superposition, a slice of branchial space is a superposition. Some lump of branchial space. If you're looking at a region of branchial space, that is a superposition of quantum states. The individual nodes in the multi-way graph are like quantum eigenstates, and you're looking at a superposition when you're looking at a region of branchial space. So that's the way in which superpositions arise, and the way in which people this kind of the whole. So for example, yeah, I mean, I think that's the best thing to say. And when you have things like destructive interference, what's kind of happening is that you're sort of routing two geodesics to opposite ends of branchial space, where no completion that an observer could make could bring those geodesics back together again. And so the photon has gone to these two different parts of branchial space, and it will never be brought back together to be something that can be, so the two pieces are kind of lost to each other, and that's the qualitative reason why you're getting destructive interference. Now, in terms of quantum causal orders, I don't know about these. Jonathan, do you have anything to say about this?
Yes, yeah. So this is something that we looked into a bit in this more general context of understanding kind of resource limitation in these models, kind of related to what Alex was asking earlier. So as I understand, assuming we're talking about the same thing, as I understand, indefinite causal orders in quantum information theory, it is a way of treating essentially causal order as being a resource like, more conventional quantum information resource states, like entanglement states and things like that. And so then what you can have situations where you have a system where the actual details of the causal partial order are in superposition. And in fact, in the algorithmic causal set paper that I think I linked in the chat at some point earlier, we investigated a particular instance of this, so a particular instance of a multi-way system where the individual states are not themselves, the individual state vertices do not represent bulk states of a hypergraph. Instead, they represent sort of indefinite causal partial orders up to some point of evolution. Now, of course, so in a sense, what you see when you take a slice through that multi-way system is
just to mention the buzzword. Jonathan is talking about causal multi-way graphs. That's the buzzword, where every node in the multi-way graph is a causal graph of the things above it.
Right, exactly. So at each step, you're introducing a new event, and that event is either in the causal future or space-like separated from the events that came before. And so exactly as you say, you construct a multi-way system where it's essentially each vertex is a complete causal graph. And so then what that allows you to probe is essentially superpositions of possible causal order relations, superpositions of possible conformal structures of space-time. And that has a bunch of implications for understanding things like spin foams, in which one is also looking essentially at a discrete way of representing superpositions between states of space-time, but also gives one essentially a way, if one treats these state vertices as being like a resource state for the purpose of some quantum, for the purpose of a quantum computation, then this essentially becomes a very concrete way of representing these quantum causal orders. And then of course the condition that the system be causal invariant is effectively an asymptotic, almost like an asymptotic safety condition, an asymptotic consistency condition that says that even though on a small scale, one can appear to have essentially indefinite causal partial order, in some appropriate limit, the causal partial orders all become isomorphic. There's much more to say about that, but yes, that is something we've investigated.
Okay, thanks a lot.
The thing I want to say about this and many other questions is these are very interesting questions. This is a big, complicated model that we're building, and we are just at the edge of investigating these things, and these are really interesting things to talk about. And we'd be happy to interact more about these things. So don't make Jonathan make you think that he's solved it all. He's made great progress, but it's
great. So can I just kind of check that I understood. So in your theory, you assume that if you have two kind of events, you assume that the causal order is predetermined or no. So you don't. Do you assume that the causal order is predetermined in the kind of most abstract level?
You have to understand our model is in some sense a deterministic model, but not deterministic in the way people usually think of determinism. So the multi-way graph is completely determined. Given that a particular underlying rule, it completely determines the multi-way graph. But your experience of the universe may correspond to some particular quantum observation frame in that multi-way graph, and that will your experience. And for example, the causal graph defines a partial ordering, right, between events. It does not define a total ordering. Your foliation defines a total ordering. Different foliations, including different quantum observation frames, can end up with different orders for events. It's different for things which are in anti-chains in the partially ordered set. You can have different orders. Things which are time-like separated are in a determined order. Did that make sense?
Yeah. All right. That's very interesting. Thank you very much.
There.
Fei Meng, if you have a question.
Hi, Stephen. Thanks for your inspirational talk. I have one question about the number of dots. In the example you show, I feel that the number of dots grows increasing. The number of dots grows increasingly as you update them. But if I have a real live objects such as a cup, it seems that when I observe it, it does not expand. So how should I understand in your model?
Yeah,
Even
good.
The triangle theory.
Right.
Triangle expands. Okay.
Good question. Right. So a couple of things to say. So in you can absolutely have situations where you have multiple possible rules, some of which expand the number of nodes and some contract the number of nodes. So there's nothing about the intrinsic structure of the model that says the number of nodes has to increase. However, we don't really know. So I've been, in a sense, trying to avoid the Einstein mistake of, of saying, oh my gosh, my theory says the universe should expand, but it doesn't, so to speak. Trying to avoid that mistake. And I don't know for sure whether the correct way of thinking about this is, in fact, that these microscopic structure is expanding rapidly, but maybe the topological obstructions that represent the things that we experience are not, are robust with respect to that, even though the underlying fabric of space is expanding. Now, one kind of funny thing is people say, is space discrete or continuous? Here's a bizarre possibility. Bizarre possibility is, let's say it is correct that it's expanding very rapidly, then it could be the case that you say, I'm going to prove that space is discrete. Okay, I'm going to set up my experiment. By the time I do that experiment, space will have subdivided to the point where it will no longer be discrete at that level. So it's like epsilon delta proofs in calculus, but you'll never see that space is discrete because of the way you measure it. So I don't know if that's correct or not. I think that a lot of what's remarkable is that all the things we conclude about relativity and quantum mechanics and so on don't really depend on these issues. I'll mention one other thing. We have some estimates of what the elementary length might be. I'm not sure the estimates are correct. They're kind of hokey, and they assume that there's that we do not have this rapid expansion of the structure of space. They assume that there's some kind of equilibrium in the rough magnitude of the amount of space, so to speak. In those estimates, the elementary length is around 10 to the minus 90 meters, so quite small. We do understand from this why the Planck energy has always seemed bizarrely large. It's off by a factor of 10 to the 120 in our models. So our elementary energy is 10 to the 120 smaller than the Planck energy. It's because the Planck energy would be coming from the causal graph rather than the multi-way causal graph, but the thing that's actually relevant is the multi-way causal graph. Another slightly depressing feature of our models with respect to these estimates of actual magnitude of things is the question is, there's a certain part of what's going on in our models that's essentially just maintaining the structure of space. And then there's things like all the particles that exist and all the energy that exists and so on that we perceive in the universe. And so you might ask the question, what fraction of the effort of the universe is put into things that we care about? And at least in this kind of hokey estimate of magnitudes of things, about 1 part in 10 to the 120 of the effort of the universe goes into anything other than the maintenance of space, so to speak. I might mention, by the way, if you're an interesting thing about this maintenance of space question is if you ask about, can you travel faster than light? Traveling faster than light, we have light cones, which are defined by causal cones in the causal graph. But the question of how those causal cones map to the actual structure of instantaneous structure of space is not a trivial question. And so what you realize is that if you can hack the structure of space in the same way as you might be able to, choose which molecule to sit on if you want to be taken across a room much faster than the speed of diffusion, so to speak, you can by doing enough computation, you could imagine, at least conceptually, if not practically, that you can, chart a course that finds what amount to sort of tunnels in, well, I've been calling space tunnels that allow you to go faster than light. So it's just another fun feature. It's one of the fun features of having a discrete structure of space-time is that you get phenomena like that.
Yes, I see. So there could be many phenomena that can really be put into experiment test, right?
I hope so. I mean, this is one of our next big challenges is figuring out. So, are there things that happen when, in rapidly rotating black holes, are there places where there are only a few causal edges involved so you can tell they're discrete? Are there places in, well, for example, one big thing I didn't mention in our models is one of probably many big things I didn't mention. There's a maximum speed of light. That's the mapping between causal edges and the spatial structure. There's also in our models a maximum speed of entanglement. So there's a maximum speed in branchial space. So that means that there's essentially a causal cone in the multi-way in branchial space that has a maximum speed. So in a given amount of time, you can only go a certain distance in branchial space. And so that means there's not only a maximum speed of light, the maximum speed of propagation of information in physical space, but a maximum entanglement speed. In our really hokey estimate, it's about 10 to the 5 solar masses per second. So that would mean that if you see, for example, the merger of two very large black holes, you might expect that some features of that merger were limited not just by the speed of light, but by maximum entanglement speed. And that's something you might be able to observe. And that there are a whole bunch of other things which are potentially observable. But one of the challenges is, even once you say, okay, we might have dimension fluctuations, what actual consequences does that have for a microwave photon propagating for 1 billion years? That's a non-trivial piece of physics to figure out. And so we're just about to start a really serious effort to try and understand the phenomenology of a variety of phenomena, which, even though we don't know the scale, even though we don't, all we need is one number. If we knew the maximum entanglement speed, the elementary length, or any one of a whole bunch of other things which are closely related, we would know the scale of things, and we'd be able to say where you should expect to see certain phenomena. But without that scale, we're stuck trying to find sort of scaleless features, or stuck trying to say there are these phenomena and you might see them, but we don't know at what level.
I see. Thank you. Thank you very much.
Carlo, your turn.
Unmuting myself. Yeah, thanks. In fact, what I wanted to ask is, and to comment, is this coming out in the previous questions. But let me articulate nevertheless. This was useful, Stephen, because you gave a big overview of a possible vision, how things could be. But at the end of the day, we're physicists, right? So the point is that what we can actually say about the world that teaches us something more about reality. As far as we know so far, reality is well described by generativity and the standard model. So it seems to me that a new idea, a new formalism, a new approach, more than say, okay, in principle this can be explained, in principle that can be explained, in principle that can be derived, can only do two things. One is a clean reformulation of what the theories of physics we have. And you are claiming that you have a derivation of general relativity from your model, which is fine, it's great, it's interesting, in fact I want to look at it. There are also many reformulation of general relativity, right? Regge has the discrete version of it, and there's there are numbers of it. So good. It's going to be interesting if it differs from general relativity, and yours differs from general relativity.
It does.
And so of the many ways of rethinking general relativity, there are certain many in the market. It seems to me that it only becomes different in the moment in which you say, look, if you rethink this in this way, there is a discrepancy. This is a discrepancy, and that's what you might look experimental.
So for example, to be concrete there, just to, I mean, obviously what we're doing is, in Regge calculus, one already has topology of space. We don't have that. We're just looking at pure connections without any distance information or any topology. But a place where ours differs is we can derive corrections, higher order corrections to the Einstein equations. So exactly. In our models, so exactly. For example, we can see that we know those corrections, we don't know the value of those corrections.
Right. So I think this is all becoming interesting in the moment in which there's a phenomenon in which you can say, look, I have a specific prediction which is different from GR. This is it. Can we go what I'm saying is that it's relatively easy to put a huge picture of what could be. The hard point of physics is then go down to the details. I mean, there are things we don't know, of course, about the universe. We don't know what happened at the center of a black hole or at the end of a Hawking evaporation.
Look, I think the main thing that
there's a big jump of what you've been talking about and going down to physics, seems to me.
But I mean, so at some level, I think the big success and the surprising success is how well this formalism works. And one of the things that I've always taken as a test for physical models of anything, is how much do you put in versus how much do you get out. And if it was the case that we put a bunch of stuff in and then we say, oh, we have to glue on this piece to deal with quantum mechanics. We have to glue on this piece to deal with general, to deal with black holes. We have to glue on this piece to deal with angular momentum and so on. So far, not a single thing has had to be glued on. That is, given the underlying formalism, all we're dealing with is, these, rewrite rules for hypergraphs, elements, relations, categories, however you want to say it. Given only that underlying structure, we are finding that we can derive that it is inevitable, not just that we can derive, not just that, if we pick the dimension right and we set all the little parameters up correctly, then we can get this. But it is inevitable that we'll get general relativity. It's inevitable that we get quantum mechanics. It's inevitable that we get finite dimensional space. We don't know that we'll get three-dimensional space. We can't show that. We know that it's inevitable that a computationally bounded observer must perceive a finite dimensional space, but we don't know that it's three. But so I think that the thing that is both surprising, rather beautiful, and I think significant is that from so little you get so much. Now, the question of can you connect it to the this sort of moment where, so right now I view us as making theoretical predictions. That is, can we reproduce general relativity? Can we reproduce the known predictions about black holes? Can we reproduce features of quantum field theory and so on? We're doing really well at that, much better than I expected. I mean, the fact that it looks like we have a practical way of doing numerical relativity, that's really pretty interesting. I mean, that's, I think, one of the things that might happen. It's always, I'm a pretty serious student of the history of science, and so I'm always amused by the way things actually evolve. But I could imagine a situation where people use the methods that are in Jonathan's paper for doing actual numerical relativity, and they say this is great for doing numerical relativity. Of course, I don't believe the model that's underneath it, but it's great for doing numerical relativity. So in other words, you can, but the first step is to show that we can correctly make theoretical predictions. Now, the next thing, as far as I'm concerned, is, are there qualitative phenomena that that our model suggests that were not expected before? One of them is dimension fluctuations. So our model, we don't know what the magnitude is, but our model suggests that the universe isn't precisely three-dimensional, that there will be fluctuations, and possibly those fluctuations are complementary to curvature fluctuations. Possible you could even reformulate general relativity in terms of dimension change rather than curvature of space. I'm not sure, but in any case, that's a qualitative kind of thing. Look for dimension fluctuations. There are more specific things. For example, we suspect that when you have correlations okay, so one of the things that happens in a black hole is just as there is a causal horizon that is associated with the ordinary causal graph, there's a horizon associated with a multi-way causal graph. There's essentially there's sort of a horizon. Well, essentially what happens is that I think the qualitative picture is that you can't, the entanglement horizon can be outside the causal event horizon. And that has presumably a bunch of consequences for understanding black hole information kinds of questions. But the qualitative picture, I think, is that if you're inside the entanglement horizon, you cannot form a classical thought. Essentially, there's no way to have an observer, just as the observer is sort of frozen in time in terms of sort of ordinary space-time, the observer is sort of frozen in terms of branch time. And so the observer can't correlate these sort of quantum threads to form a classical thought. But in any case, the question of whether we can make specific predictions for things. So here's one of the questions I don't know the answer to yet. So the question is, are there any scaleless predictions we can make? Einstein was pretty lucky because he had a factor of 2 prediction that he got wrong originally, which is also a lesson to us all in terms of how one does these calculations. But, he had a scaleless prediction that didn't require knowing the value of the cosmological constant, for example. I don't know if we're going to have scaleless predictions. I think there's a possibility that we'll have a scaleless prediction for correlations in photons in orbit around black holes. It's possible. It's rather similar to the deflection of light around the sun. I think we might have a scaleless prediction for how that will work. But in other cases, there are predictions with scales. There are predictions that are qualitative, just saying there might be dimension fluctuations. You can look for those, things like that. But this is, it's obviously important and highly interesting to try and take this model and turn it into something where you can make specific predictions. I think the higher order corrections to general relativity is an interesting one, because that one, somebody's been working on that. You get the analog of a Knudsen number in fluid dynamics. You get essentially a point at which you start seeing, you start seeing the effect of discreteness of space on curvature fluctuations. I don't think that those will be observable, but I'm not sure. And maybe in sufficiently rapidly rotating black holes close to criticality, maybe that's observable. I'm not sure. This is yes. There are many challenging things to do, and I think it's. I mean, the thing that to understand is the actual formalism is simple in description and very complicated to work out, and very beautifully makes use of a lot of these ideas from mathematical physics, but it isn't a kind of simple thing where you go from oh, there's this model. Okay, immediately we can make this prediction. Maybe there is, but we haven't figured it out. But it doesn't look that way. You can make these qualitative predictions, like there might be dimension fluctuations, but I don't, there isn't a quick way to say, from this model immediately we can make this prediction. It's hard work.
Okay, thanks.
Ale Capurso, would you like to ask your question?
Yes. Hi, Stephen, and thanks for your interesting presentation. I'm coming from an engineering background, so I really appreciate this computational lens through which you are interpreting space-time and physics. Basically, in your model, you are addressing the rules and the computational rules that elaborates this information in a kind of discrete time, which could be like a thick present. I was wondering if, beside the reasoning on the simplification of the rule of the computational simplification, so going to the basic rule, you were thinking of also elements of how the space-time information is, let's say, stored or compressed, because beside the simplification or finding the most basic rules in terms of algorithm, the other side of basically information theory is how I basically store and save this information and compress, manage this amount of information. So I was wondering if you were thinking about these aspects, and if there are relations, maybe given the fact that you were describing the emergence of space as a foliation in this thick present, if there might be a connection in, for example, black holes you were mentioning before in this kind of information packaging, but from your theory. And also connected to this aspect, if this information is basically considered in this storage as local or global. I mean, when we look at the graph, we see all the different branches and connection, but we are looking at a global picture. In the computational aspect, you were mentioning cellular automata and parallel computation. Do you believe in your model, in your theory, actually the emergence comes out thanks to a global perspective of information, then resolves locally, or starts locally and then resolves globally?
Right. So first thing to say, obviously, is there's no substrate. It's not like the universe is being run on some other computer, so to speak. I mean, we are simply giving a description of a way to think about how the universe works, and it is interpretable by us as something computational. Now, in terms of, is the universe being efficient in the computations it's doing? The answer is computational irreducibility is the measure of how efficient or not it's being. So in a sense, general relativity, the possibility of general relativity is a sign of vast inefficiency in computation in the universe, because general covariance is basically a statement that the universe is utterly wasting its time working out all those different cases because they're all equivalent according to general covariance. So one thing to understand is, insofar as we can make statements about physics, those are signs of redundancy at an information theoretic level. So in a sense, one of the things that I think is sort of surprising about the universe is if it was just computational irreducibility, we will be able to predict nothing. The universe would be made of these very small components. Things would be happening in the universe. To predict what the universe would do, we would essentially just have to run the universe. The fact that we can exist and have a coherent life in which we predict things is a consequence of the fact that there are slices of computational reducibility. In other words, in effect, pieces of redundancy in the computation that's being done by the universe. So in a sense, we are the beneficiaries of those slices of redundancy. Now, what kinds of redundancy can we find? Probably our physics is not the only possible set. Undoubtedly, our physics is not the only possible set. I mean, when you think about, communicate with the extraterrestrials, with the alien intelligences, do they have, at least they live in the universe, we say. So they must have the same physics, but I don't think that's true. I think our notions of things like I think our notions of space and time are pretty specific to our size in the universe. The fact that, we typically, our brains process information very slowly compared to the speed of light over distances that we tend to look at things on. And that's why we kind of think of the universe as consisting of space that exists at a sequence of moments in time and so on. So but now in terms of the relationship between, for example, actual practical computing and things like reference frames and redundancy and so on, that's actually a pretty important thing, because in parallel computation, we humans have a really difficult time thinking about computations that happen in parallel. We have a pretty easy time, well, we can have a reasonably easy time saying, this happens, then this happens, then this happens, and so on. But if we say there's 100,000 things happening and they all happen asynchronously, we don't know what order they're happening in, but something happens in the end. We have a very hard time thinking in those terms and writing programs that operate in that kind of context. One of the things that's coming out of these models is having a way to use essentially the ideas of general relativity to have a way of slicing what's happening in a distributed computing system. And by the way, I mean, there's a whole sort of translation dictionary. So if you know databases, the notion of eventual consistency is the notion of causal invariance. Eventual consistency of distributed databases is the same idea as causal invariance, as an example of one of the correspondences. All right, let's see.
Yeah, thanks for your clarification. Can I just get back on the fact you were mentioning the idea of different scales, that things could happen differently at different scales. This maybe could be connected as well to the redundancy you were mentioning before. Do you think probably there is the chance that all this information that we perceive basically, as you said, at our scale, from a computational perspective, actually is elaborated in parallel, but at different scales, and then the sum is the result of what we actually see. So for example, the vast distances among the galaxies are somehow processed in a more efficient way due to the scale factor on which you apply the computation.
One of the things, right. So one of the things that was necessary for me in terms of coming up with these kinds of models for physics is, for me, computation is a valuable thing. It's hard to do computations. Computers, you spend money running, big computer jobs and things like this. One of the things I had to get used to was the idea that the universe is an outrageous, profligate waster of computation. That the universe is just spewing out huge amounts of computation. For example, in this multi-way graph, it's computing all of these different paths, most of which are equivalent and irrelevant. But nevertheless, as a way to think about what's going on, I think it's, one of the sort of intellectual blocks for me had been kind of coming to terms with the fact that imagine the universe is just doing ridiculous amounts of computation. To achieve even very little, the universe is computing tons of stuff. And in the end, the thing that we perceive from all of that computation is something quite simple, but the universe did a huge amount of computation to get to that point. So I think that's my current view of how to think about it. And if you ask, is there in principle a way to compute? Well, the laws of physics, as we know them, are a story of finding ways to make more efficient the computation. So if what's really going on is that at this underlying level, there's this computational irreducible thing happening at 10 to the minus 90 meters or something, and in the end, we see the celestial mechanics of planets. Well, the celestial mechanics of planets, we don't have to, fortunately, compute all those details of things happening at 10 to the minus 90 meters. We can have this effective theory that operates on a much larger scale. The possibility of that effective theory is a feature of there being a certain degree of computational reducibility. And that's, so our laws of physics are the story of the sense in which the universe is inefficient in its computation. The fact that we can have laws of physics and that the universe appears to behave in regular ways is right there kind of a statement that the universe is not being as efficient as it could be in computing the things it has to compute. This is a philosophically complicated thing, and I'm rushing this, so but
no, without being too much philosophical, it's usually talking about nature. It's all about efficiency, and it's strange that you consider the universe as a computational, let's say, efficient in terms of simple rule, but not efficient in terms of many calculations that basically lead to nothing.
Oh, well, it's even worse than that, because in what I suspect is happening is the universe is running all possible rules. It's even more absurdly inefficient in computation. So in other words, and what's happening is we are looking at a particular slice of this rulal multi-way graph of the running of all possible rules. So in a sense, the universe, while each individual rule, you might say, is a simple computation, absurdly large numbers of them are being run to produce the experience that we have of the universe. It's like an awful lot of effort is being put into creating the universe as we see it.
When you talk about computation, you think about information that it's actually a quantity. But if this information as a quantity diverges, basically, or is inefficient, then also if we consider information and energy as basically connected, you have also a divergence in the energy needed to compute this.
No, this isn't right. See, in our models, we actually have a very concrete view of both computation and energy. So in our models, energy is actually identifiable as kind of the amount of, it's identifiable in terms of this flux of causal edges, and it is closely connected to the actual details of what's happening in the computation. And most of the energy in the universe is in a, okay, so here's another point, that, in traditional sort of views of the relationship between quantum field theory and general relativity, there's sort of been a problem that the 0-point energy of quantum field theory is, there's lots of energy there. Why doesn't it have a gravitational effect? Why doesn't it curl our universe up into a small ball, right? That's been a sort of a long time issue. In our models, that effort, the sort of the quantum mechanical processes, the quantum fluctuations are the thing that knit together the structure of space. I think that's true of other people's models too these days, but probably for exactly the same reasons. But so the thing that the vast majority of the energy in the universe and the computation in the universe is spent maintaining the structure of space. Only a small part of it is things that seem significant to us in terms of our perception of what's going on in the universe. But anyway, there's probably, you're probably asking something slightly different, but we should probably move on these are interesting issues.
Thanks for your clarification. Maybe we can take it offline. I don't want to waste all time for everybody.
I'm late for something else myself too. So, but I would love to hear more questions here, please.
Okay, we'll try to make it short. There are still 4 questions. So Marius.
Hi, thank you, Pierre, and Stephen. Thank you very much for the fantastic talk. We try to be brief. It's also related to what many people are asking in the chat. So I'm more from the physics, from general relativity background. And what is very striking in your statement is to say you recover the Einstein equations. And that's what people are, I think, trying to understand. And there has been many things that have been mentioned, super interesting. I think it would be helpful if you could tell us what are the organizing principles, because you need some input, right? You have to put something in, and then you will find.
Right. So basically, what goes in is you have elements, relations, rules. That's it. You have relations between elements, and you have rules that take limited numbers of elements and limited numbers of relations and make transformations for them. And that's the whole story of what goes in. Now, conceptually, what goes in is you think about that as a computation. There is this phenomenon of computational irreducibility. Computational irreducibility leads to effective randomness, leads to the perception of something as being, as far as the observer is concerned, it's effectively random. That leads to ergodicity. That allows you to take continuum limits. That's one part of the story. I guess another part of the story is, how do you actually construct a geometry from this hypergraph, these collections of relations between elements? The first way you do that is by just looking at the structure of the graph and saying distances are determined by graph distances on the graph. That's ultimately not the way you should be doing it. You ultimately should be doing it by thinking about propagation of photons or whatever else, but that's a good proxy for how you start off. I mean, I think you're kind of asking perhaps for, can I give you the
principles? Sorry to interrupt. I was asking if there is like one or two big principles, like general covariance or strong equivalence principle that goes as input.
I think the ultimate principle is this principle of computational equivalence. I think that's the thing which, in the end, everything percolates down to that principle. If that principle was not true, none of this stuff would work.
In like simple words, what is one request?
Okay, so this principle will at first appear to you completely irrelevant to physics. Okay, but the principle is, when you have a system based on rules, there's a question of how sophisticated is the computation typically done by that system. And the statement of the principle of computational equivalence is, when what's going on in the system isn't obviously trivial, it will be of equivalent computational sophistication. So in other words, all these different systems, whether they're little cellular automata, whether they're hypergraphs, whether they're Turing machines, whatever else, all these systems will do computations that are ultimately of equivalent sophistication. In other words, what it's saying is, above some extremely low threshold, everything is doing the same level of computation. And that's the principle, which in the end, I mean, there's a bunch of tentacles that come out from that, but that's in the end, I think I guess you need that, and you probably it's fair to say that you need some notion of how to think about it. It's a good question you're asking, and I was meaning a number of months ago to kind of try and write down in sort of axiomatic form what are the fundamental things that we're assuming, because there's very little, and it really, in the end, actually there is one other assumption. There's one other assumption, which is that observers are computationally bounded. So the combination of these assumptions, the principle of computational equivalence and the computational boundedness of observers, those are critical assumptions. So in other words, that the observer is not capable of sort of redoing all this irreducible computation, that the observer is seeing only this larger scale stuff. That's a critical assumption. And so that, I mean, I suppose well, yeah, maybe Jonathan, do you have a crisper version of this?
Well, I can give a perhaps slightly less abstract version that's specific to the case of general relativity, which is that there are three axioms that one requires in order to produce that derivation. One requires causal invariance, this statement that the causal graphs associated with all possible evolution histories, all possible paths in the multi-way system are isomorphic. One requires asymptotic dimension preservation, which means that if you construct a geodesic ball in one of these hypergraphs or the causal graph, or you construct a geodesic cone in the causal graph, then the exponent of the leading order term in that sort of discrete volume expansion should converge to something finite. And the third requirement is a weak ergodicity hypothesis, which says that if we set up an arbitrary hypersurface in the causal graph, the net flux of causal edges through that hypersurface converges to zero in the continuum limit. And I'll gloss over a lot of the technical detail, but essentially the reason why those three axioms give you the Einstein field equations in the continuum limit is, so what you do is you say, I construct I project a discrete space-time cone in the causal graph in some time-like direction. And then I can look at the growth rate of that volume. And as Stephen already mentioned, the growth rate of that volume we can show quite easily, even in the discrete case, is sort of, there's a correction term to the dimension sort of estimation, which at the second order is given by the time-like projection of the discrete Ricci curvature tensor. And so then what we can do is we can say, well, what would need to be satisfied in order for the causal graph to converge to a finite dimensional Lorentzian manifold? So then what you actually want is for that dimension anomaly, as we call it, to converge to 0 in all directions. So essentially what you get is a constraint that says, if I average out over all possible time-like projections and across all possible events in the causal graph, then the change in that quantity has to converge to 0 as the causal graph gets larger. So the thing that allows you to make all of those projections is causal invariance, because anytime you make a different time-like projection, you're essentially choosing a different a local coordinate basis in your space-time. And the thing that says that the causal structure is invariant on the choices of local coordinate basis is causal invariance. You need the asymptotic dimension preservation, because that's the thing that forces this quantity to converge to 0. And you also need the weak, okay, and so then that gives you essentially already a discrete form of the Einstein-Hilbert action, just a thing that says if we sum essentially this Ricci scalar that we recover by taking implicitly taking the trace by computing this average over the Ricci curvature tensor, that we want some variation of that sum to converge to 0. Then the final thing you need is you have to have some way of exchanging that sum for an integral in the continuum limit. And the thing that analytically justifies that exchange is this weak ergodicity hypothesis. So as long as one has a rule, and we have examples of rules that satisfy these conditions, and instances are given, for instance, in the numerical relativity paper. But so what that derivation shows one is that as long as those three axioms are satisfied, causal invariance, asymptotic dimensionality preservation, weak ergodicity, the Einstein field, well, the extremization of the Einstein-Hilbert action and therefore the Einstein field equations are an inevitable consequence. What Stephen is then explaining at a kind of higher level is how those axioms are in fact corollaries of this much more general principle, which is the principle of computational equivalence. But
you're correct. That's a much better level, Jonathan. I should have explained it at that level. I mean, those three things that Jonathan mentioned follow from principle of computational equivalence and the assumption of computational boundedness of observers, but they follow in a somewhat more abstract way. Looks like we have a couple more hands up. Yeah, please.
Yeah. So next is David Rideout.
Hi, Stephen. Very fascinating talk. I was thinking a bit about the relationship between your theory and causal set theory. So in your theory, the fundamental object is this, well, atoms of space and some sort of relationship among the atoms, something like adjacency or some such thing. Well, in causal set theory, the fundamental object is something very close to your causal graph.
That's correct.
Causal relationships between
our events are like
events, if you like.
Yeah, right. Our events are the same kind of thing as the events in causal set theory. Now, the difference, the main thing, and Jonathan wrote a paper about this, is the fact that we essentially have an algorithmic generator of those causal graphs. We're not generating them according to a probability distribution. We essentially have an algorithmic generator of causal graphs.
Right. So I'm just wondering if you could comment on why. So your story is about computations on these spatial structures, this spatial hypergraph. So why are these spatial hyperrelations the fundamental entity?
Okay, that's a good question. Right. Why don't we start from the causal graph? That's kind of right. Yes, exactly. I have wondered this myself. Could we just start from the causal graph? I think the answer is I don't see a good way to do that. In other words, it's what we've got is this kind of natural way to generate, we've got the stuff that the universe is made of, so to speak, and then we've got the things that are happening in the universe. And it seems useful, and I can't really give you a great argument for why. It seems useful to start from the sort of static data structure of the stuff in the universe and then ask how it behaves and derive the causal relationships that way, rather than starting from the causal relationships. Although the things that you guys have learnt from starting from the causal relationships and looking at the consequences of large, partially ordered sets, those things are directly applicable to the things that we're getting We just happen to have a generator for those causal graphs, as opposed to just saying, we're picking a causal graph from a space of all possible causal graphs. But I have thought about this in the past, and I think I maybe have had some better arguments for this conclusion, but I certainly wondered, could we just start from the causal graph? And I wondered that, I think, okay, actually, here's my point. Yes, I have a better way to say this, sorry. The key realization is time is something significant. So what I mean by that is, in our models, time is the inexorable progress of irreducible computations. So in other words, we're not saying, oh, all of space-time just exists. We're saying to make space-time, you have to go through this immense amount of computational effort growing from one moment of time to the next, so to speak. So whereas you might say, well, just give me all the events and I'll connect them together. What I'm saying is to get from one event to another is this sort of irreducible computational act. And so that's a reason why it makes more sense to say, rather than saying, give me give me this whole network of events, because that's essentially asking for a thing that takes an infinite amount of computation to produce. Whereas what I'm saying is, if you can start from the spatial hypergraph and then say, okay, what does it do? You just, each successive micro step in what it does is a bounded amount of computation. So I think that's I think that's the basic argument, is that basically what we're doing is we're being honest about the fact that time means something, so to speak, that we actually have to, that time is some actual process that has to go on, rather than that just time is a coordinate and we throw things into things at different coordinates in space and time. So yeah, so I think that summarizing, I think it's basically that there is computational irreducibility, and that is what corresponds to the passage of time, and that time isn't just a coordinate, so to speak.
And so why is the computation about space?
Okay, that's a good question.
Why space?
Right, well, so space is what we have. That's what our universe seems to be made of. Interestingly, I've looked at computational systems where the computation is not about space. So actually these things called combinators, which were invented 100 years ago, last December, which were actually the very first model of universal computation, they involve tree-like structures. They're essentially tree symbolic expressions. And you can go through the whole development that we've done on those, and they don't have a notion of space. They have this bizarre kind of tree-like notion of space. They don't have this notion of extent in the same way. Strangely enough, a lot of other systems that I've looked at, I've just been looking at another one that's another centenary system looked at by a person called Emil Post. These are very simple string-based systems, which I thought had no notion of space. But actually, I realized a few days ago that they too have an emergent notion of space. But so, it's not self-evident that there would be an extent of space, so to speak. It's that is in a sense a feature. Now, all these statements about principle of computational equivalence, this rule-eel multi-way graph, and so on. The fact that we attribute to the universe a rule that has a notion of extent of space, I think, is saying as much about us as it is saying about the universe. But that's a different issue. But this is, given that we think of the universe and we model physics in terms of space, that's why I think it's a reasonable thing to sort of put something that can represent spatial extent in there. But probably not necessary. I mean, I don't know how to untangle. In a sense, what we're trying to do is we've got a very low-level machine code. We're trying to connect it. We're trying to get far enough up in the kind of chain of things to be able to connect it to existing physics, and to go from combinators that far up is even further than we're trying to go, so to speak. So that's but yeah, no, I mean, I wondered for decades actually about sort of what is the right underlying stuff to try and make these models out of. And I will say one thing that sort of is in the end an embarrassment to me is the following thing. So what we ultimately have, these hypergraphs and these relations between elements and so on, these are essentially symbolic expressions. And what we essentially have is a great big system that looks at transformations between symbolic expressions, and that is our universe. Okay, so the embarrassment is, I've been building computational languages for 40 years, and they are based specifically on the idea of transformation rules for symbolic expressions. Yet I didn't make that connection. In other words, but the reason I didn't make that connection is when you have transformation rules for symbolic expressions in a computational language, all the pieces of that symbolic expression are labeled with things like plus and times. They have a meaning to us. What the model of physics is something which is a completely meaningless symbolic expression, where everything which would normally be a plus, it's a times, it's an x, it's a y, those things are just atoms of space that have no meaning to us. They're purely just things that have an identity, but they don't have a name, they don't have a meaning. And in a sense, what we're doing is just this, this great big symbolic expression structure, and which I should have been able to see decades earlier, so to speak, because that's in a sense, what I was been doing is kind of the with human meaning version of the same kind of model that we now have in, two things. I mean, first of all, in using symbolic expressions to do things that are humanly meaningful, they're comparatively small. The idea of a symbolic expression with 10 to the 400 nodes, all of them meaningless, was a little bit hard for me to get to. But that's what these models are.
Sorry, Stephen, do you mind if I jump in just for a moment?
Go ahead.
Yeah, sorry. So David, on your question in particular of which I think is a very interesting one, and which is one of the questions I tried to address in this paper about the relationship between the stuff that you guys do in causal set theory and what we're doing, is you might just think, okay, well, I have an abstract rewriting system defined over a class of hypergraphs, and I can use that abstract rewriting system to construct a causal set. And so at some level, I could just view the hypergraph as being nothing more than a notational convenience. I just view it as kind of the grist for the mill of generating some causal set, right? And I don't endow it with any greater significance. And you can absolutely do that. And the causal sets you get out have the same asymptotic properties as the kinds of causal sets that you would get by, say, Poisson point processes or classical sequential growth dynamics and those kinds of things. But actually, it turns out there are places where having the hypergraph structure is quite important. And which, I mean, okay, one other thing that I would like to clarify is, at first, when you say you have a spatial structure, to a relativist, that sounds very odd, right? That you're by endowing space with some kind of significance, that's very anti-covariance. But actually, it turns out that's not really a problem, because there isn't just one hypergraph, because there isn't just one updating sequence, right? There are many possible updating sequences, many possible updating orders, yielding different, potentially non-isomorphic spatial hypergraphs. So in effect, each possible hypergraph is analogous to a possible space-like hypersurface subject to a particular gauge choice, where our analog of a gauge choice is a particular choice of updating order. The significance of that is that then when you want to, say, for instance, define a Cauchy problem, it becomes much, much easier, for instance, to do a canonical 3+1 decomposition of the metric if you already know essentially what the spatial metric tensor is, right? So I'm aware, because I've looked a bit into the literature, but obviously I don't know it as well as you do, that this is a problem that you guys face in the context of causal set theories. For instance, how do you estimate space-like distances? And I know that you, for instance, have, there's this estimator I think you co-developed with Walden. There's the Brightwell-Gregory estimator. There's this more recent Eichhorn-Surya-Verstegen estimator that's based on like antipodal point, using antipodal points on causal cones of particular volumes to estimate space-like distances and so on. What we get from having the hypergraph structure is a much, much more direct way of estimating space-like distances and therefore endowing the hypersurfaces with a spatial metric tensor. And I did both analytical and numerical experiments, or analytical and numerical tests, comparing these different dimension estimation approaches, and the hypergraph approach turns out to be more robust. It's kind of unsurprising because we have, we're kind of cheating. We have more information to start with than you guys have in a causal set. But and the place where, as I say, where that becomes significant is if you want to do something like numerical relativity, one of these situations where you actually want to define, initial data on a Cauchy surface and then construct maximal Cauchy developments and things. If you want to construct an ADM decomposition, it helps to be able to have some kind of robust way of equipping your space-like hypersurfaces with a metric tensor. That's just one, and there are other places like in the context of dimension estimation where having the space-like distances as well as the time-like distances helps a lot in being able to prove convergences of certain dimension estimators, places like that. So it's not you can view it as being a completely useless appendage. If you only want to care about the causal structure, in a sense, it is a useless appendage, but there are very, very sort of practical places where it becomes useful, like in defining Cauchy problems, like in doing space-time dimension estimation, those kinds of areas.
So my impression from what you're saying is that it strongly constrains the set of partial orders that you get out.
Yes.
And somehow
Yes.
that constraint is, I don't know, you're suggesting that's a physical one or something like that.
Yes.
That's a
yes.
good thing. Somehow.
Yes, that's the basic idea.
Right. Anyway, it makes the calculations easier.
Right. I mean, the arbitrarily thrown down partial order is not what we're dealing with. We're yes. And by the way, relativistic invariance, for example, is something which is sort of inevitable from our way of generating these. It's not that you have to worry about, oh, am I going to get a partially ordered set which is going to show the right Lorentz invariance properties. That's something that's inevitable when you have causal invariance and you're generating the sets in the way that we're generating them.
Okay, interesting. Thank you.
No, we want to, I mean, a lot of these questions, by the way, point at people asking about how the things that they do relate to things we do, and we're really interested to understand those things. And we're just yakking about the way that we think about things, but we really would like to learn more from people, because as I say, the thing that I'm, I would say personally particularly excited about is the extent to which the things we're building can be viewed as kind of a Rosetta Stone for connecting a lot of different approaches in mathematical physics that already exist, and where lots of things have been developed. I think we're providing a machine code. Other people have already built high-level languages for talking about certain aspects of this. We just, we're just providing a machine code that perhaps helps knit these things together.
I see. Okay.
So there's the last question. Pablo, if you want to ask.
Hello, can you hear me?
Just about, yes, you're a little bit faint.
Okay, thanks. So thanks a lot for the talk. I wanted to ask about unitarity. So to me, what you have is a non-deterministic rewrite system on graphs, a confluent one, but nonetheless a non-deterministic system. And although Feynman used to say that quantum mechanics is more or less probabilities with a minus sign, those minus signs, they are there for a reason, and it's like, a unitary matrix it has a structure. It's almost like something stochastic perhaps, but the signs, the phases, they are arranged just so that you can reverse things back in time. And this is something that I really do not see happening from what you've showed us.
Right. So first thing is actual unitarity. That is because the magnitude of our quantum amplitudes is determined by path counting, it's inevitable. In other words, the path counting, you're just counting how many ways can you get to this particular node. And because you're just, the paths have to go somewhere. So it's inevitable that you get unitarity at that level. I think what you're also referring to is something about time reversal invariance, which is a whole different thing. Of course, actual time reversal invariance isn't true for the physical universe. But if you're asking, does our system get to something which has equilibrium in the sense that there is apparently the same kind of behavior going forwards in time as going backwards in time, like thermal equilibrium? The answer is our computational irreducibility story makes it pretty much inevitable that to a high degree of approximation, you will have something which is in equilibrium in the sense that it will appear to be the same going forwards in time as going backwards in time. But the formal notion of unitarity in quantum mechanics, I think, is guaranteed by the path counting way that we interpret the magnitudes of quantum amplitudes. Maybe I'm missing something.
I get that because, I mean, the whole story about quantum mechanics is precisely that there may be many ways to reach a point, but they may all cancel each other due to sign reasons.
Right. But the point about cancellation, so this is why I'm talking about the fact
wrong, and then everything cancels out and you just get to the null vector. So
right. So what happens, the point is, in quantum mechanics, we're used to saying there's a complex number associated with every quantum state, okay? That complex number packages two things. It packages a magnitude and a phase together. In our models, the origin of the magnitude is very different from the origin of the phase. So the magnitude is determined by this path counting. The phase is determined by position in branchial space. So when you say there are these two paths and you say they cancel each other out, What's happening to us is those two paths wind up, that their path weights are just fine, but they end up being at opposite ends of branchial space. And being at opposite ends of branchial space, an observer can never pull them together to basically conclude that you're getting a, we don't yet have a great way to say this, but formally it's that you can't, those two things can't be made. What is the right way to say this? I mean, the qualitative picture is just that you get destructive interference because you can't be pulling together those two different paths into the thing that you observe. Maybe, Jonathan, this is your interpretation of quantum mechanics, so you better have a better way to say this.
Right. Okay. I mean, this is actually a general point that came up a lot in the chat, so it's perhaps worth addressing it in a bit more detail about this question of time reversal symmetry and things like this. So exactly as Stephen mentioned, so when we talk, for instance, when we talk about time symmetry in GR, the Einstein field equations are already a continuum limit approximation to something that's going on in our models. So what one is effectively doing is one is coarse graining out all of the microscopic details of the connectivity of the causal graph and just equipping it with one tensor field, with the Ricci curvature tensor, and talking about how that changes. And talking about, placing dynamical constraints on that curvature tensor across the causal graph. So you can have the situation where the microscopic rules, the rules that act on the microscopic structure of the network, are irreversible. But if one coarse grains out by a sufficient degree, the rules, the effective rules that you see are reversible. And as Stephen mentioned, this will happen essentially anytime you get a sufficiently ergodic behavior, which of course is what we use for GR. So you have the situation with the Einstein field equations derivation that you get time symmetry of relativity, even if the model itself does not obey microscopic time symmetry. Now, a similar thing happens.
Say that a different way, Jonathan, just to say, I mean, in your average cellular automaton, the rules may be irreversible, but you quickly evolve to an attractor, and the dynamics on the attractor is reversible. The effective dynamics on the attractor is reversible. And it's the same thing here. Please.
Right. Yes, no, that's exactly right. And the reason why that happens, as I say, is effectively anytime you define an effective theory like this, and in the context of our models, GR, QM, these are all effective theories, you are coarse graining out by certain microstates, and irreversibility of those microstates doesn't really matter at that point. Okay, so as I say, the same thing is really happening in our derivation of quantum mechanics, and the way, and it's worth mentioning, by the way, that the version of unitarity that we prove in our model is not the standard algebraic form of unitarity. It's actually this more general PT symmetry version of unitarity, where the underlying evolution operator does not have to be algebraically unitary, but it can still be the case that ket psi naught is recoverable from ket psi t for any t, for any t greater than naught. So we're using the kind of Carl Bender, Dorje-Brody approach to handling that kind of PT symmetry. And so again, that emerges as a consequence of a coarse graining story. And in that context, it becomes quite easy to understand this point about GD6 ending up on two opposite points in branchial space destructively interfering. Because what you're saying is, recall that the distance metric in branchial space is this common ancestry distance. So effectively, the more distant a pair of states are in a branchial graph, the more completion rules, i.e. the more equivalence relations one has to impose in order for those states to collapse to a common eigenstate. Okay, so what that means, that means if you have two states that are close by in branchial space, you only have to impose maybe have to impose one equivalence relation to force them to be equivalent, and so that will preserve some amount of information about what those original states were. If they're on opposite ends of branchial space, which means they're very distantly removed in terms of their common ancestry, that means that you have to impose an arbitrarily large number of equivalence relations, you have to introduce an arbitrarily large number of completion rules to make them merge. And each time you impose those completion rules, that's a coarse graining. You're losing information every time you do that. And if they're at opposite ends of branchial space, that corresponds to the situation where by the time you force them to merge, all of the information is lost. And that's, and so effectively you get a completely information-theoretic version of how destructive interference works. That's the qualitative picture. Suffice it to say, there is a mathematically formalized version of this picture, which works by, as was mentioned, treating these multi-way evolution graphs as being objects in a dagger-symmetric monoidal category, in which case the Hermitian adjoint operation as encompassed by this dagger structure is just given by the reversal of evolution arrows in the multi-way evolution graph, and it's not too difficult to prove that operation satisfies the requisite compatibility conditions of a dagger structure. But that's, at least at a qualitative level, that's what's going on. You're coarse graining out by so much that any information about what the states originally were has been lost.
Right. Okay, it's a bit funny to me that you should recover reversibility as a kind of emergent behavior when I would, in the hierarchy of physics theories today, I would put quantum mechanics as the microscopic fundamental one, not the one that you should see emerging. But okay,
right. Well, this is what happens after 100 years later. Quantum mechanics seems fundamental. That is and perhaps yes. I mean, one of the conceptual things that we're doing is to say there is a machine code which is under quantum mechanics, so to speak, rather than taking the point of view quantum mechanics is at the foundations and then building up from that. I mean, it's not obvious what would be true. I think that but what's exciting is that it seems to actually work to think about quantum mechanics as an emergent theory. But it's certainly not obvious, and this question about reversibility and things like that, to me, that I don't view that as being a particularly fundamental property, partly because because of lots of things I've seen in computational systems where it emerges, but it wasn't put in there to begin with. So that to me is not one of the ones that seems like it's a very I haven't been looking.
Coming back home, so I'll cut the video.
What's that? No, I noticed you're mentioning superspace, so Wheeler. Yes, indeed. Those things are. I'm always interested in the history of ideas, and I was a little disappointed to discover when I finally got a copy of Wheeler's book that came out of those superspace, which those superspace things came out of, that at that time he was convinced that neutrinos were gravitons, which is, I guess, why that book has not been seen more. But it's a very interesting book. And yes, there are absolutely connections to that, as to many other of these things. I am actually really super late for something, even though this is really interesting.
So there are no more questions. So this is the end of this seminar. It has been more than 2 hours of very intense discussion. So I would like to thank once again Stephen Wolfram for having accepted our invitation. That was really kind of you. And I would like also to thank all of you who have asked questions or just attended this seminar for your participation. So the next QISS virtual seminar will be in about 3 weeks on March the 11th, and we will have a philosopher, Doreen Fraser, talking this time. So see you next time, and take care.
Nice to meet you all. Bye-bye.
Bye.
Yeah. Bye.